the last of our review material, I want to remind ourselves of what the definite integral from a to b of f of x with respect to x is. I'm not thinking of how we calculate these things, the antiderivative trick. I want to go back and think about what the definition of that symbol was in the first semester. Starting with the interval that starts at x equal a and ends at x equal b, we're going to select a positive whole number that we'll call n. We're going to make a list of x numbers in the following way. We're going to call a x number 0. We're going to call b x number n, which obviously depends on which value of n we picked. And between them, we're going to have a collection of x numbers that get steadily larger as the index on the x number increases. A will be x0, which is smaller than x1, so x1 is to the right of x0. x1 is smaller than x2, so x2 is further to the right than x1 is, and so on and so forth until you arrive at x equals b, which is what we're calling x number n here. This is called a partition of the interval from a to b, and we represent it with the capital Greek letter delta. This divides the interval from a to b up into n chunks. Since these x's need not be evenly spaced, these individual chunks may not be the same width. We will make up a name for the width of each interval. The first of the smaller intervals starts at x0 and ends at x1. Its width is x1 minus x0. I'll call that delta x number 1. The next subchunk of my interval starts at x1 and ends at x2. I'll call its width delta x number 2, which is just going to be x2 minus x1, and so on. For each index j, 1 through n, I'll have a width of the corresponding subchunk delta xj, which will be x number j minus x number j minus 1. Amongst all of these different lengths of subintervals, there has to be one of them that is as big as any of them are. We're going to look at the biggest width of a subinterval, the maximum delta x number j, for j equal 1 through n. We'll make up a symbol for that. This is pronounced the norm of the partition delta. For us, the major use of this is if the norm of the partition tends to 0, all of the delta xj's have to tend to 0 also, since each one of them is no more in size than the norm of the partition. This will give us a convenient way of saying all of the delta x's tend to 0. Within each subinterval, for example, subinterval number j, select an x number or a number out of the values of your independent variable, if you're using some other letter. I'll call this, in this case, x value. I'll call it c number j. I could pick it down close to the left end, close to the right end, in the middle, somewhere in the interior. It turns out that I don't care exactly where the cj is located at. For each subinterval, I'm going to evaluate function f at this cj, and I'm going to multiply it by delta x number j. In a moment, we'll remember what the interpretation of that is. Since I have n of these subintervals, I'm going to add up all such contributions. This is called a Riemann sum back in the first semester. There is an unlimited supply of different ways I could chop the interval up into smaller pieces. There is an unlimited number of ways that I could pick the Cj within each subinterval. So the collection of all of these Riemann sums is an enormous set of things. Out of that enormous collection of Riemann sums, if I allow the norm of the partition to approach 0, if I let all of the spacings, all of the delta xj's approach 0, that limit either exists or it doesn't exist. If it exists, then the value that I get back from it doesn't depend on the exact details of how I did my partition, which will be very convenient for us in a moment. If that limit exists, we make up a special name for it. We call it the definite integral from a to b of f of x with respect to x. This, if you go back and you look in chapter 4 of the Calculus 1 book, this is the definition of the definite integral. The definition does not involve the antiderivative in any way. We have a technique for calculating these definite integrals that does involve the antiderivative, though. This is what we called the first fundamental theorem of integral calculus. If f is a continuous function on the interval from a to b, and if g is an antiderivative of function f, then this definite integral, which is this limit over this huge number of different ways you could do the Riemann sum, turns out to be easy to calculate. Find the antiderivative of f, calling it g right now, evaluate it at the upper limit of integration, evaluate it at the lower limit of integration, and subtract. This is how we're going to actually calculate these definite integrals, but we're going to be looking at problems where the way we set it up is we think about the definition of the integral first, then we turn it into one of these type of problems, which we then evaluate with the antiderivative trick. Assuming that we can calculate this integral, if the function f only takes on positive values, then this integral that we're calculating is an area. This is your first motivation for studying this back in Calculus 1, so I want to return to that just for a moment. I'm going to think of the graph of y equal f of x, starting at x equal a, ending at x equal b, and what I'd like to think about is the area under the curve between x equal a and x equal b. Based on what you know from Calculus 1, this is just going to be the integral from a to b of the function, but I want to think about why that is exactly. I'll think of forming a partition of the interval from a to b, so a will be x0, b will be x number n, and in between I'll have x1, x2, x3, out to x number n minus 1 in increasing order of size. I'm going to think about one of these subintervals, subinterval number j, where j could be 1 through n. This starts at x number j minus 1 and ends at x number j. This is a magnified picture of subinterval number j, along with the piece of the graph that lies above that subinterval. Somewhere within this subinterval, I'm going to select an x number that I'm going to call C number j. There'll be a point on the graph of the function f to go with that x equals cj. When you're on the graph of function f, the y-coordinate is the function value. So the y-coordinate of the dot that I've drawn in is function value f of cj. The width of subinterval number j, xj minus xj minus 1, is delta x number j. If I make all of the delta xj's very small and the function is continuous, it doesn't have much of an opportunity to change its value very much on subinterval number j, so I can pretend that it's more or less a constant value. If I figure out the area of the dotted rectangle that I've drawn in, it's the vertical height, f at cj, multiplied by the horizontal width, delta xj. With the thought that this approximation becomes better as you take the delta xj's to be smaller, because on each subinterval the function will change even less than it is now. So returning to my picture, what we've done is we've got an estimate for the area under the curve that goes with one of these little subintervals. I'll have an estimate like this for j equal 1, 2, 3 out to n. So if I want an estimate for the total area, I need to add up all of these individual contributions. But this is just one of those Riemann sums. If I want to make my estimates better, I should make all of the delta x's j very small. To make my estimate perfect, I should let them get arbitrarily close to 0. In particular, the biggest of the delta xj's should approach 0. So to get the total area, I'll take the limit as the norm of the partition tends to 0 of the sum j equal 1 to n f at cj delta xj, but you'll remember this is the definition of the definite integral. So this is equal to the integral from a to b f of x dx. It's worth mentioning that there's a pattern to this. This isn't always going to be areas that we talk about, but the pattern will be the same. I'm going to have a sum. I'm going to have some independent variable. Right now it's x, but it need not be. I'll have widths of subintervals of my independent variable, in this case the delta xj's. I'll have some function that depends on an independent variable value, in this case cj. In this case it's an x number out of subinterval number j. I multiply the function value by the change in the independent variable that goes with it. I add up all of those things. I take the limit as the biggest of the delta xj in this case, it could be other letters later, tends to 0. Anytime I have a limit that looks like that, I will automatically write it this way. F of cj, or whichever letters we use, f of cj becomes f of x. Delta xj's become dx. The limit of the sum symbol becomes an integral sign, and the a and the b are determined by the smallest and biggest x numbers that are involved in the set of x numbers you're interested in. For the definite integral to exist, as I look at all conceivable partitions and all conceivable choices of the CI's, or CJ's in this case, as I allow the norm of the partition to tend to 0, I have to get the same number regardless of the details. This means if it's convenient for me, I can select a certain type of partition, and if the integral exists, then this partition will produce the value of the integral. So what I'm thinking of is I'm going to use a uniform partition. I'm going to pick my x numbers so that the delta xj's are all the same number. The width of the entire interval is b minus a. If I decide to divide this up into n equally sized subintervals, the width of each one must be 1 over n times the width of the interval from a to b. Since all of the subintervals are going to be the same width, I'm not going to bother putting an index on them. I'm just going to call the common width of the uniform partition b minus a over n. x1 is going to be bigger than x0, bigger than a, by an amount delta x. On the other hand, x2 is going to be delta x bigger than x1 is, and x1 was a plus delta x. x3 is going to be delta x bigger than x2 was. So x3 is delta x plus delta x plus delta x bigger than a. X number 3 is a plus 3 times delta x. The pattern should be obvious. X number, a certain index, is going to be a plus that index times delta x. Subinterval number j ends at x number j and begins at the preceding x number j minus 1. So I can write down a formula for subinterval number j also. And again, delta x is b minus a over n. As mentioned previously, not only am I free to pick the partition any way I want, I'm free to pick the C numbers any way I want within their corresponding subinterval. In the examples that I look at shortly, I'm going to pick the C number j to be x number j. I'm going to pick it to be the right-hand end of the subinterval. Using equally sized subchunks has another advantage here. The spacing on the uniformly spaced grid that I've got, delta x equals b minus a over n. When I take the limit to get the integral, I'm going to want the delta x to approach 0. For a uniform grid, all I need to say is that the n needs to become indefinitely big, and that'll do it for me. So if I use a uniformly spaced grid, when it comes time to take the limit, I'm just going to say, take the limit as n tends to infinity. All of this seems like just complete nonsense here. Let me show you now that we can calculate something that previously we didn't know how to calculate. I want to find the limit of a certain sum. That sum is the sum j equal 1 to n of 3 plus 2j over n whole thing raised to the fourth power multiplied by 5 over n. On the face of it, this doesn't look very hopeful. If you look at the pattern, though, we said that we're going to use as our Cj x number j, which is a plus j times delta x. So I'm looking at a plus j times delta x. I'm looking at the sum that I've got, and I'm trying to think, is there something in there that I could think of as being a plus j times delta x? And obviously, the thing that suggests itself to me is the thing that I'm raising to the fourth power has the same general form as a plus j delta x. It's a constant plus j times something that hopefully I'll interpret as delta x. If I rewrite 3 plus 2j over n as 3 plus j times 2 over n, I see what I should do about the a. The a should be 3. This is going to be my lower limit of integration. If I want to continue matching the pattern, I have a factor of j, I have a factor of j, I have a factor of delta x, I have a factor of 2 over n. If I make delta x equal to 2 over n, then these two expressions will be the same. The reason that I really want to know the delta x, though, is not because it's going to figure directly into the integral that I get at the end. I've got my lower limit of integration x number 0, which is a. A is going to be 3. I need to know the upper limit of integration also. Generically, b is x number n. So I'm going to write my formula down when j is equal to n. If you plug j equals n into our 3 plus j times 2 over n formula, we find out that b, which is xn, is 3 plus j equals n times 2 over n, and the n's cancel out. b is 3 plus 2, which is 5. There's my upper limit of integration. Now, what we've done so far is we've accounted for the fourth power of 3 plus 2j over n, but there's also this factor of 5 over n floating around out there. I have to figure out what that is in terms of delta x before I can write my integral down. So the actual factor that you've got running around in the problem is 5 over n. Delta x is not 5 over n. Delta x is 2 over n. So I need to express this in terms of 2 over n somehow, but that's easy. This is 5 over 2 times 2 over n. You can see that by canceling the 2's back out. The only reason that I want to write it that way is the 2 over n is delta x. So this factor of 5 over n at the end is actually equal to 5 halves times delta x. So this limit that we're looking at, the limit is n tends to infinity of the sum j equal 1 to n, 3 plus 2j over n raised to the fourth power times 5 over n can be written in this form. Limit of a sum of some expression that involves Cj multiplied by delta x number j, which in this case is the common value delta x. This is the definition of an integral. The limit of the sum symbol turns into an integral sign. The delta xj's, which in this case there's only delta x, turns into dx. X is the variable of integration here. In everything that remains, stop writing cj down and start writing x down instead. And the only remaining issue is to put the upper and lower limits of integration in, but we have figured out that the lower limit of integration was 3 and the upper limit of integration was 5. This is now a calculus 1 problem. I can take the factor of 5/2 out because it's a constant factor. If I can find an antiderivative for the continuous function x to the 4th, I'll just stick 5 and 3 into that antiderivative, subtract, and we'll have our answer. An antiderivative for x to the 4th is 1/5 x to the 5th power. I'll be able to cancel the 5's out. The result is going to be 1/2 times 5 raised to the 5th power minus 1/2 times 3 raised to the 5th power, which after doing the arithmetic turns out to be 1,441. So what we've done here is we have a limit of a sum problem, this problem. By thinking about it in terms of a uniformly spaced partition, we are able to see what the biggest and smallest possible x values involved were. Those told us the limits of integration. That let us turn the 4th power part into just a c number raised to the 4th power. We did have to figure out what to do about the 5 over n, but that turned out to be a minor issue. Once we did all of that, it turned it into this. To calculate this limit is the same as calculating that integral, and that integral is easy to do based on what we learned in the first semester. This is a prototype for the kind of problems we're going to be looking at. We may look at areas, we may look at volumes of one type or another. We will look at length along a curve. We will look at work problems of various types, and the strategy is always going to be the same thing. We're going to look at our problem and somehow write it as a limit of Riemann sums, turn the limit of Riemann sums into a nice integral, and then use the antiderivative trick or some other method to figure out what the value of the integral is. This is our only trick in Chapter 7. We'll do this over and over and over again. This is kind of an abstract looking thing, but hopefully it's not too complicated. This is everything I wanted to say about this. Next time, we'll start actually looking at a simple problem that we've already solved once back in the first semester, but now we'll solve again. Until then, I hope everyone's having a good day. I'll talk to you again soon.